Okay. Having studied the most general form of the solution to the wave equation, which is y of x and t equals f of x minus vt, actually minus or plus, depending on the direction of propagation, let us focus on some simple examples. We know the simplest and yet very common type of oscillation is called simple harmonic oscillation. Wave is caused by an oscillation which propagates down the medium. Suppose the source of this oscillation is simple harmonic. For example, consider the wave propagating on a string. Okay, it is caused by my hand holding one end of the string up and down. What if my hand moves up and down in a sinusoidal fashion, in other words, like a sine-cosine function of time? Then the wave that's produced is also called a simple harmonic wave. In a simple harmonic wave, every particle in the wave medium oscillates in a simple harmonic way. So basically you have a whole bunch of simple harmonic oscillators propagating and the pattern of simple harmonic oscillation propagates down the string. That's called a simple harmonic wave. A simple harmonic wave is an example of what's called a periodic wave because the wave repeats itself. Okay, of course the sine of cosine function are periodic functions. So let's look at a diagram for that. In a simple harmonic wave, here is a snapshot of the simple harmonic wave. Okay, at a certain moment, this is the orientation of the string, this is the oscillation. Okay, at a certain moment you take a snapshot, this is what you get. You have a sine or cosine function. In a sine or cosine function, as you go from this is called a wave crest, here's the next crest. Okay, the distance between these 2 points. That's how the wave repeats itself from one location to another location. This length, this distance, is called lambda or wavelengths. You can think of the wavelengths as the period of the wave over space, not over time, but over space, between one point of the wave and another point of the wave, such that these 2 parts of the wave are exactly the same. Okay, it's not just between these 2 highest points, also between this point and this point, or between the 2 lowest points. Anyway, between 2 corresponding points. Alright, now if you focus your attention on one particular particle in the wave, okay, not just taking a snapshot of a whole string over at one moment, rather you focus your attention at one particular particle and give it some time, and then you plot the displacement of that particle over time, not over x. Then you find that this particle, which represents also other particles because they have very similar motions, executes a simple harmonic motion. Okay, it executes a simple harmonic motion and it goes up and down over time. And of course, these 2 points have a time difference. Over such a time difference, the motion repeats itself, so that's a period t of that simple harmonic oscillator. So what you have here is lambda and t. Okay, lambda is the period over space and t is the period over time. Now, how are they related? Well, imagine this wave. Okay, imagine this wave. Here's the snapshot in one moment. Let's look at the snapshot at the next moment. So at the next moment, the wave propagates forward, right? So it looks like this. Okay, you look at how this particle moves. All right, look at how this particle moves. This particle moved down, right? Moved from here to there. Now, look at another time later. Okay, the wave propagated even further, so this time the wave will now look like this. So the wave pattern traveled forward, and look at each particle. This particle moved further down to here. See? It moved further down to here. And of course I can keep on drawing, so the particle went first down, 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 then and stop it here and go up, 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 up. Okay, my question is, what happens when the particle goes all the way from the top, going down and back to the top? This is the time it takes for the particle to repeat itself one cycle, right? That time, of course, is t, right? Meanwhile, what happened to the wave pattern? Well, during the meantime, this crest must be replaced by another one coming from here, so that after time t later, the wave again looks like this red curve. All right, so that means the wave has advanced from here to there. It has moved a distance, lambda. Okay, remember the speed of the wave is v. Okay, so basically over a time period t, the wave moved forward a distance lambda with a speed v. Using distance equals speed times time, we find that lambda equals vt. This is the important relationship. Now, let us look at how we can write this general function in terms of sinusoidal form, sine or cosine function. Okay, so let's do that. Let's say y equals, okay, it's a sine or cosine function, right? So let's say sine. Let's say sine function. It doesn't really matter, sine or cosine. Okay. Remember, x and t must be connected like this. You cannot break x and t apart. X must be followed by positive or negative vt. Okay, that's how you get a traveling wave with a speed v. Alright, so I have x minus vt, right? Okay, except there's a problem. And the problem is x minus vt is not dimensionless. You know, you cannot use this directly as an argument of a sine function. The argument of sine function is just an angle and it's totally dimensionless. So what do? Well, you must multiply this whole thing, this whole argument, x minus vt, by some sort of constant. Okay? And what is that constant? Well, we call it k, for example. Okay, so you must use k to multiply this whole thing, x minus vt. What is the unit of k? The unit of k is such that it must cancel with the unit of x, so that k times x is unitless. Okay. Not only so, but this overall sine function is also dimensionless. It cannot match with the dimension of y, which is, of course, length. So how do you solve that problem? Well, just like in oscillation, we must also have an overall constant in front of it. Okay, that overall constant is the maximum value of the sine function or cosine function, and we call it a. That a, as you know, is the amplitude of the oscillation in that wave. Okay, so we have three parameters here. We have a, we have k, and we have v. We know exactly what a is. A is the amplitude of each particle oscillating in the wave. We know exactly what v is. V is the propagation speed of that wave. But what about k? That looks like a new variable, right? How does one find k? Well, k is a new phenomena, and it must be related to lambda, because after all, lambda is a new phenomenon that has to do with wave that we didn't have to deal with before. Okay, so let's take a look at what k means and how to find k. Alright, let's take a look at a snapshot of a wave at a given moment t. Okay, look at these 2 points here. They differ by wavelengths lambda. Okay, t is the same because that's a snapshot taken the same moment. The phase angle after the sine function between here and there, they must differ by 2 pi because that's how the wave repeats itself after a phase angle changes by 2 pi. So this phase angle between here and there, delta phi must equal to 2 pi. Meanwhile, delta x between here and there is lambda. What about delta t? Oh, well, that's 0 because you take the snapshot between this point and that point at the same moment. Okay, now phi equals k times x minus vt, right? The phase angle expression, and therefore we say delta phi equals to k delta x minus v delta t. Now delta x equals lambda, delta t equals 0, so this is just equal to k lambda. Between here and there, what's that delta phi equal to again? 2 pi, okay, because the wave repeats itself. This tells us what lambda is. Lambda equals, k equals 2 pi over lambda, and that's what k is. We call it wave vector.